Hello everyone, so we can continue with non-homogeneous linear systems, and today we are going to discuss the method of undetermined coefficients. This is very similar to what we had for high-order equations, so you might have some intuition. First of all, let me remind you the definition of non-homogeneous linear system. This is our system. This is a linear part, homogeneous part, and this is a non-homogeneous part B. Both x and b are vector functions, and A is a matrix. And the previous lecture was about variation of parameters. Any equation of this form can be solved in the following way. You just apply this formula where psi is a fundamental matrix of the homogeneous part. So it seems like there is nothing to add about non-homogeneous linear systems, because we have the method that always works when A is constant. However, the method of undetermined coefficients applies to many cases when B is not too complicated, and is a huge simplification. In the method of undetermined coefficients, you don't integrate, you don't compute psi, you don't invert it, so this might be a huge shortcut. However, it doesn't apply to all B. Variation of parameters apply to all possible B, and the method of undetermined coefficients only applies when B are combinations of things like that: exponentials, cosines or sines, and polynomials. Same as we had for higher order equations. There might be no cosine, which means b equals 0, or no exponential, which means a equals 0, or no polynomial, so it could be just exponential or just cosine. And then the method of undetermined coefficients applies. First of all, we'll actually repeat what we had for high-order equations, this formula with a complementary function and particular solution. So, a general solution of the non-homogeneous equation is given by complementary function plus particular solution. Complementary function is a general solution of the homogeneous equation, and xp is one particular solution of the non-homogeneous equation. To prove this, you just make sure that this formula works well. So I'm going to substitute this x into the equation and make sure that it works. So x prime is xc prime plus xp prime. Now xc by definition satisfies this equation, x prime equals ax, so I just write axc here, and xp prime is equal to this, to the right hand side of the non-homogeneous equation for xp, because we know that xp solves the non-homogeneous equation. And then if you look at this expression, you will see that this is just ax plus bt, so x is indeed a solution. I have proved that this thing is a solution. How do we know that this gives all solutions? You can notice that this has all possible initial conditions. We know that xc is a general solution of x prime equals ax, so for different constants over here you will have all possible initial conditions, and then the sum will also have all possible initial conditions. Since you can satisfy all initial conditions, you can solve your equation with any initial condition, so due to existence and uniqueness theorem you have found all solutions. Okay, so we have this theorem for the non-homogeneous equation. We can find xc by solving the homogeneous part. The only thing to find is one particular solution of the equation. It remains to find just one solution of the non-homogeneous equation. Undetermined coefficients method gives hints how to find it. suppose that components of the vector b, all components of the vector b, are expressions like that, with one and the same a and b for all components, and possibly different p. And suppose that this a plus ib is not an eigenvalue of a. This is called non-resonant case, similar to higher order equations. Then when you try to find a particular solution, you should try the solution whose components, all components of this vector xp, will be combinations like that, where degree of q's, q1 and q2 will be smaller than the degree of p, where this polynomial has same or smaller degree than p. So this is kind of a general case. I'll write out several particular cases because you will never have both p, exponential, and cosine. This gives you too much undetermined coefficients here and is hard to solve. So suppose that b is, say, a 2 vector that only involves e to the power 3t. Then for xp, you should try e to the power 3t with some coefficients a and b. Once you write this out, you should substitute this xp into your equation and try to solve a and b. These a and b are undetermined coefficients. And this will work if this case is non-resonant, which means that 3, this 3 over here, lambda equals 3, is not an eigenvalue of the linear part of the equation. This is the equation, the condition of non-resonance. Let's take another b. Let's take b that only has polynomials in it, t and 1. So the higher degree of the polynomials is 1, which means that for x you should try polynomials of degree 1. In this statement it means that you don't have exponentials and don't have cosines, you only have polynomials. I would say that a equals 0 and b equals 0 as well, so lambda is 0 for this case. If this 0 is not an eigenvalue of the linear part, of the homogeneous part, then for this b you should try this x. Then you take this xp and substitute into the equation and try to find a, b, c, and d. And then if b is some vector that only involves sine of 2t and cosine of 2t, then for x you should try combination of cosine and sine. Each component of xp should be such combination. And here lambda is plus or minus I. Like using this formula you can see this bt here inside the cosine, then it comes out here, and lambda is plus or minus ib. So you should check that this plus or minus I is not an eigenvalue of the linear side, and this is what you should try for xp. Let's have an example. So this is my example. This is my linear part, this is my homogeneous part, and this is a non-homogeneous part. My solution will be the complementary function plus one particular solution. Complementary functions should solve the homogeneous part, and I just found the eigenvalues and eigenvectors and used the eigenvalue method to write out the solution. This is my complementary function. It solves the homogeneous equation without b. And then, since b only has e to the power t in it, so it is e to the power 1 multiplied by t, lambda is 1. 1 is not an eigenvalue here, and it doesn't appear over here in the formula. So this is a non-resonant case, and I should choose xp. Both components of xp should be constant by exponential. Now I should substitute this into the equation to find a and b. This is x1 and x2. So this is x1 prime. I substitute it into the equation. And then this is x1 plus x2. This is x2 prime. This is 3x1 minus x2, and this is my b. Now you can see that you have e to the power t everywhere. You can divide by it, and this is the system on a and b. You can solve it and find a solution. So the general theory tells you that the solution exists. The previous theorem tells you that you can always find such a and b. You will always be able to solve the system. Now you just write out the solution. It is the complementary function from here and the particular solution from here. Now you know a and b and can substitute it here. A and b are just minus 1/3 and minus 1, and this is the only choice. So that's how to use the method of undetermined coefficients in the non-resonant case. After a small break, we will talk about the resonant case.